So, pinakita ko ulit ito. Dito yung correction. At yun, 40 degrees north latitude on July or August. Kasi yung table sa is for 40 degrees north. In case na lagi sa Philippines, 14.5 degrees north latitude. So, mayroong conversion nun. Convert nyo yung table or factors, multiplier. Andun din sa, ano, sa, andun sa table sa ASRE ng 27. Saka, meron din doon sa binigay kong Carrier Design Manual. So, meron din doon ng calling load calculation. Halos similar yung mga table na ginagawa nila. Okay? Okay. So, wala para doon sa, sa carrier yung itong ibang latitude. Saka dun sa personal naman, wala naman. Sa ASTRAY, sinagay lang is 40 degrees north latitude. Pero may ibang mga lugar na hindi sa 40 degrees. Pwede 14.5. So, polary, mag-assume muna tayo ng 40 degrees. So, meron yan na conversion talaga. Nasa isang book, yung book. Kasi yung calling heating load din yun, calculation by, hindi mo ko kung meron kay splitter kasi second version yun. Yung ginamit ko is yung kay Doroy and Cuba. Andun yung mga table, tapos meron dun note na conversion. Kita ko na yun dati. So, dito is 40 degrees. Saka na yun. Ano na kayo? Practicing na kayo. Is alam nyo na gamitin. Dito hindi pa. So, 40 degrees muna tayo. So, example, wall na tayo na. Okay. So, yan. So, example, the wall has a 4 inches brick exterior, 1 inch air gap, and 8 inch concrete block wall. So, dito Pilipinas, sa Pilipinas sa kasi ata ano, blocks. Pero may mga gumagamit yan dito. Normally lang sa atin sa lupas. Calculate the overall U value of the walls based on the material used and the standard set forth in ASPEC. So, ito. CMU is concrete masonry unit. 8 inches CMU, 1 inch airspace, and 4 inch face brick. Asan yung outdoor? Dito, face brick siya. Ito yung indoor sa kabila. Yan. Nasolusyon yan, di ba? Tabulation, construction material. Outside resistance, air resistance. Yan, meron siyang wind speed. Yan. Itong inside air resistance is still air. So, kaya magkaibang value niya. Air film niya. 4 inch face brick, 1 inch air gap, 8 inches CMU. Concrete block wall. So, select mo yung L value doon sa table. May table doon sa ASLAY. Yan ang value, 0.33, 0.43, 0.91, 0.02, 0.6, add mo 4.38. So, yung value is reciprocal. So, i-add mo to, yung reciprocal nito, yun yung U value niya. Okay. Ito yung individual U value. So, ibig sabihin, wala naman ito talaga. Walang kwenta to. So, ito lang ang kailangan mo yung total. Okay. So, alisin na lang natin siguro. Okay. Two ideas are important here. Dito, the first is the idea of thermal resistance. Heat energy flows from hot spaces to cold spaces and it increases as the temperature difference increases. The material which separates the temperature extremes has a certain resistance to energy flow. When the resistance is high, the rate at which energy flows through the material is low. When the resistance is low, high energy flow rates are expected. We insulate walls to lower the rate at which energy flows through the walls. Insulation increases the thermal resistance or R value of the wall. The second important idea is the idea of the heat capacity of the building material. Heat capacity is a measure of material's ability to store a heat energy. Metals tend to have low heat capacities. When heat energy flows through a metal, it changes temperature quickly. On the other hand, stone or cement has a much higher heat capacity. When heat energy flows into stone, it changes temperature very slowly and tends to store the heat energy. Passive solar homes include a large mass of stone, rock, or other materials with high heat capacity. Passive means yung mga walang motor. Okay? Walang active movement. Hindi yung mga walls, pinto, yan, passive yan. This thermal mass will heat up during the day when the sun shines. At night, when it is colder, energy can be drawn from thermal mass. Nalabas. It is interesting to note that water has a very high heat capacity. Open water inside a house might create humidity problem, but in our atmosphere, the high heat capacity of water has a significant effect on moderating temperature and on the weather pattern in general. Kaya yung iba, pag malaki yung basin mo, yung sa laboratory, nilalagyan ng exhaustion para di ma-expose dun sa room. Next, solar load through glass. Solar load through glass has two components, one conductive and two solar transmission. The absorbed and then conductive portion of the radiation through the windows is treated like the roof and walls where LCLTD values for standard glazing are tabulated in ASRI Fundamentals Handbook. So, table naman ng glass. So, for solar transmission, the cooling load is calculated by the cooling load ECL factor and the shading coefficient. The cooling load equations for glass are conductive, Q glass conductive is UA CLTD glass corrected. Same numbers. Solar transmission Q glass solar is A times AC times ECL, where Q conductive is the conductive load through glass in BTA per hour. Q solar is the solar transmission load through the glass in BTA per hour. U is the thermal transmittance for glass in BTA per hour Fahrenheit, square foot Fahrenheit. A is the area of glass in square feet. CLTD is the cooling load temperature difference for glass and Fahrenheit. EC is the shading coefficient. ECL is the solar cooling load factor. Now, steps for conductive calculation. Step number 1. For the glass type used, select from as the table the overall heat transfer coefficient U. The glass is the major contributor of heat gain in commercial building. Pay attention to the effect of shading, reflective films, curtains, drapes, etc. Refer to example below. Later. Yan. Step number 2, select CLTD glass for time of interest, typically on an hourly basis. Sa chapter 28, ASTRE, table 34. Yan. Iba-ibang value niya, 8 a.m., 9 p.m., 9 a.m., 10 a.m., yan, hanggang p.m. Step number 3, corrections. Wait. So, CLTD glass corrected is CLTD glass plus 78 minus TR plus T and minus T 85. Same, where 78 minus T sub R is the indoor design temperature correction. T sub A minus 85 is the outdoor design temperature correction. T sub R is the indoor room temperature. T sub M is the mean outdoor temperature. T sub maximum is maximum outdoor temperature. So T sub M is equal to T max minus daily range over 2. Step number 4, calculate glass area from architectural plan. Step number 5, then Q glass is UA, CLTD glass corrected. Step number 4 for solar transmission calculation. Step number 1, determine the ceiling coefficient EC from Astrid and 97, chapter 29, table 11 sa glass. Step number 2, determine zone type from Astrid and 97, chapter 28, table 35B. Step number 3, determine solar cooling load factor ECL from Astrid 1987, chapter 28, chapter 36. Step number 5, 4. Calculate glass area from architectural plan. Step number 5. Cube glass solar is A times ECL times ECL. So example. So estimating U value and compare cooling load of different glass type with or without drapes. Yan. So U values can also be estimated if thermal resistance R or thermal conductivity of glass material is known. U value is the inverse of R value. So the R value is calculated as R over L is equal to L over K, where L is the thickness of material and K is the thermal conductivity. So the thermal resistance for the window with and without drapes R without drapes is R total plus R air film plus R window plus R air film inside outside. With drapes is R total plus R of drapes plus R of graph plus R of window plus R of air film. Lagi yan. So assume data thickness of glass is 1/8 inch. Curtain window spacing is 3.5 inch. Conductivity of glass is 0.81 meter per hour square foot. Conductivity of drape is 0.035. Andun yung sa mga saas there. Thickness of drape is 1/16 inch. Thickness of insulated drape is 1/2 inch R. Values from ASTRE fundamentals 2001 or 1997. Okay. So ito yung mga drapes. Curtain window spacing. Meron tayo dito R of gap. Yan. Gets niya. Spacing. So meron tayong consider na double, ito, glazing. Double glaze, single glaze. So ito yung mga R value. So inside vertical air film is 0.68. Uninsulated drapes 0.15. Insulated drapes 1.2. 3.5 is vertical air gap. Yan 1.1. Single glaze wood or vinyl frame is 1.2. So double glaze is 2. Outside vertical air film is 0.25 kasi may velocity, may wind speed. So ito yung calculating U values, get cross the series, resistance, R1, R2, R3, etc. Then with the reciprocal, makukuha mo na yung U. So ito na, mga types, different type of window drapes with shield the following result. Windows drape with single pane window, no drape. Ito yung equation niya, R total plus R air film plus R window plus R air film. Add mo yung R total is 0.68 plus 1.2 plus 0.25 plus 0.25 is 2.13. So yung value niya is simple yung reciprocal niya. Double pane window, no drapes. So our total is the same equation. So 0.68 plus 2 plus 0.15, 25 is 2.93. Reciprocal, U value. Single pane window, regular drapes. Yan. R total is equal to R of air film plus R drapes plus R gap plus R window plus R air film is equal to 0.68 plus 0.15 plus 1.1 plus 1.2 plus 0.25 is 3.38. Double pane window regular drapes. So same equation. So 0.68 plus 1.15 plus 1.1 plus 2 plus 0.25 is 4.18. Single pane window insulated drapes naman. So this is 0.68 plus 1.2 plus 1.1 plus 1.2 plus 0.25 is 4.43. Double pane window insulated drapes. Yan, magiging 5.23. So for the terms, architectural terms yan. So check namin sa definition sa ASTEC kung meron ba. Now, for single glazed window, adding drape reduces heat loss by 37%. Adding the same drapes to double glazed window reduces heat loss by 30%. Adding insulated drapes to a single glazed window reduces heat loss by 56%, 48% for double glazed window. So for single and double glazed window, both claims are approximately true. The reduction in heat loss is smaller for double glazed windows than it is for single glazed window. Now next is the partitions, ceilings, and floors. Whenever a conditioned space is adjacent to a space with a different temperature, transfer of heat through the separating physical section must be considered. So Q is equal to U A times T sub A minus T sub R C, where U is the coefficient of overall heat transfer between adjacent and conditioned space in BTU per hour square foot Fahrenheit as stated in 97, Fundamentals, chapter 24. A is the area of partition in square feet, ceiling, or floor calculated from building plans. Note yung course binabanggit dito is yung second floor, third floor, and above. Hindi kasama yung ground floor. Depende kung ang ground floor mo sa may basement. Okay? Kasama yan dito. Pag ano kasi, ground floor, lupa na sa ilalim yun. So, iba na yung temperature sa ito. Kumbaga, malamig yung ano yung lupa. Okay? So, meron siyang special treatment doon. Mababa yung U value doon. Special computation dyan. T sub A is the temperature of adjacent space in Fahrenheit. Note, if adjacent space is not conditioned and temperature is not available, use outdoor temperature less 85, less 5 degrees Fahrenheit. If the adjacent temperature is the same as the inside design temperature of conditioned space, so that is 0. Okay. TRC is equal to inside design temperature of conditioned space and degrees Fahrenheit are assumed constant. Note that the temperature TE may range widely from that in the conditioned space. This temperature in a kitchen or boiler room, for example, may be as much as 15 to 50 Fahrenheit above the outdoor air temperature. The actual temperature in adjoining spaces should be measured when possible. When nothing is known, assume outdoor air temperature less to 5 degrees Fahrenheit. Now, next is the internal cooling load. Ito. The various internal loads consist of sensible and latent heat transfer due to occupants, product, processes, appliances, and lighting. The lighting load is only sensible. The conversion of sensible heat gain from lighting, people, appliances, etc. to space cooling load is affected by thermal storage characteristic of that space and is thus subject to appropriate cooling load factors to account for the time lag of the cooling load caused by the building mass. The weighing factors equation determines the cooling load factors. CLF is equal to Q cooling load divided by the Q internal gains. Note that the latent heat gains are considered instantaneous. People. So Q sensible is equal to N times US times CLF. U latent is equal to N times QL, where N is the number of people in space, QS is QL is equal to sensible, and latent heat gain from occupancy is given by Astley 1997, chapter 28, table 3. CLF is the cooling load factor, by hour of occupancy. See 1997 as the fundamental subject 28 level 57. Bakit may hours? Kasi at the start of ang office mo is 8, ini-start mo ng 7 yung aircon. So, ibig sabihin, habang tumatagal, malamig na. So, kung magkakaroon ka ng factor, mababa. Okay? Note, CLF is 1.0 if operation is 24 hours or if cooling is off at night or during weekends. The table below gives representative rates at which heat and moisture are given off by human beings in different states of activity. Table. Ayan. Ayan. Open, this sensible and latent heat gains constitute a large fraction of total load. Diba yung sensible and latent? Ito yung representative lang naman ito. Okay. So even for short-term occupancy, extra heat and moisture brought in by people may be significant. These values are for 78 Fahrenheit room light bar temperature. For 80 degrees live temperature, the total heat remains the same, but the sensible heat value should be decreased by approximately 8% and latent heat values increase accordingly. Occupants generate both sensible and latent heat components according to activity level. The sensible heat rate increases slightly with higher activity, but latent heat increases dramatically because of greater perspiration rate needed to maintain body temperature. Occupancy heat gain values in ASPE. So ito yung representative lang, marami din pang value. Heat gain per occupant at various activities at indoor air temperature of 78 Fahrenheit. So ito yung activities, seated at rest, seated very light work writing, seated eating, seated light work typing, standing, light work or walking, light bench work, light machine work, moderate dancing, heavy work, lifting, athletics. Ito yung mga value. Total, adult male, adjusted. So, sensible, ito na yung adjusted. Adult male, adjusted kasi male, female. Sensible and latent. Ito yung natin na lang to na adjusted. Wait lang. Next is the lights. The primary source of heat from lighting comes from light-emitting elements. Calculation of this load component is not straightforward. The rate of heat gain at any given moment can be quite different from the heat equivalent of power supplied instantaneously to those light. Only part of the energy from light is in the form of convective heat, which is picked up instantaneously by the air conditioning apparatus. The remaining portion is in the form of radiation, which affect the conditioned space only after having been absorbed and re-released by walls, floors, or furniture, etc. This absorbed energy contributes to space cooling load only after a time lag, with some part of such energy still present and radiating after the lights have been switched off. Generally, the instantaneous rate of heat gain from electric lighting may be calculated from Q is 3.41 times W times FUT times FSA. Cooling load, mamaya yung symbols. Cooling load factors are used to convert instantaneous heat gain from lighting to sensible cooling load. Thus, the equation is modified to Q is equal to 3.41 times W times FUT times FSA times CLR, where W is the watts input from electrical lighting plan or lighting load data. FUT is the lighting use factor as appropriate. FSA is the special balance allowance factor as appropriate. CLF is the cooling load factor by hour of occupancy. See 1997 as the fundamental chapter 28 table 38. Note CLF is equal to 1.0 if operation is 24 hours or if cooling is off at night or during weekend. The total light wattage is obtained from the ratings of all lamps installed, both for general illumination and for display use. The special allowance is the ratio of wattage in use for the condition under which the load estimate is being made to the total installed wattage. For commercial applications such as stores, the use factor would generally be unity. The special allowance factor is for fluorescent fixtures and or fixtures that are either ventilated or installed so that only part of the heat goes to the conditioned space. For fluorescent fixtures, the special allowance factor accounts for the ballast losses and can be as high as 2.19 for 32 watt single lamp high output fixtures on 277 volt circuit. Rapid start 40 watt lamp fixtures have a special allowance factor that vary from a low of 1.18 for two lamps at 277 volts to a high of 1.3 for one lamp at 118 volts, with a recommended value of 1.2 for general application. Industrial fixtures other than fluorescent and a sodium lamp may have a special allowance factor varying from 1.04 to 1.37, depending on the manufacturer and should be dealt with accordingly. For ventilated or recessed light fixtures, manufacturers or other data must be sought to establish the fraction of the total wattage that may be expected to enter the conditioned space directly and subject to time lag effect versus the which must be picked up by return air or in some other appropriate manner. Next is the power load. Industrial and commercial applications such as various equipment such as fans, pumps, machine tools, elevator, escalator, and other machinery which add significantly to the heat gain. There are five equations in use for different scenarios, machines, and motor. So case number one, if the motor and the machine are in the room, the heat transfer can be calculated as Q is equal to 2.45 times P over the efficiency times FUM times FLM. P is the horsepower rating from electrical power plants or manufacturers' data. So 2.45 is a conversion factor. BTU per hour per horsepower hour. BTU per horsepower hour. So F is the equipment motor efficiency as decimal fraction. FUM is the motor use factor, normally 1.0. FLM is the motor load factor, normally 1.0. Note FUM is 1.0 if operation is 24 hours. In this situation, the total power is transferred as heat to load. Note again, if the machine is a pump or a fan, most of the power are transferred as energy to the medium and may be transported out of the room. For such cases, case 4 shall be used. Case 2. If motor is outside and the machine is in the room, the heat transferred can be calculated as 2545 times P times FUM times FLM. P is the horsepower rating from electrical motor, plants or manufacturer's data. It's the same. FUM is the motor use factor. FLM is equal to motor load factor. FUM is 1.0 if operation is 24 hours. Bakit? Case 2, ano na lang siya, yung machine na lang, hindi yung motor. Di ba? Pag motor and frame kasama, so ito, divide mo ng efficiency kasi andun yung source. Yung source saka yung output. So case 3, if motor is belt driven and motor and belt is outside and machine is in the room, the heat transfer can be calculated as Q is equal to 2545 times P times the built efficiency times the FUM times FLM. So yan. So yung P, multiply mo na efficiency, yun na yung sa machine mo, di ba? So P is the horsepower rating from electrical power plants and on manufacturer's data. Belt F is the belt transmission efficiency as decimal fraction. FUM is the motor use factor. FLM is the motor load factor. FUM is 1.0 if operation is 24 hours. So case number 4. If motor is in the room and machine is outside, The heat transfer can be calculated as 2545 times P over efficiency minus P, the difference, times FUM times FLM. Yung motor kasi nasa loob. So, P is equal to horsepower rating from electrical power or manufacturer's data, and F is the motor efficiency. So, FUM, motor use factor, FLM is the motor load factor. Note, FUM is 1.0, F operation is 24 hours. Yan. Note yun lang. Nasa loob yung motor. Case 5. If the motor is belt driven and the motor and belt is in the room and the machine is outside, the heat transfer can be calculated as ito, 2545 times P over motor efficiency minus P over the belt efficiency times FUM times FLM. P, horsepower rating from electrical power plants or manufacturer's data. FUM is the motor use factor. FLM is the motor load factor. The highest quantity of wheat gain shall be from the case 1, when both the motor and the driven equipment are located inside this space. The physical location of equipment is not the only governing criteria on using a particular case. An exception is taken for pump and fans to use equation in lieu case of number 1, even if both the driver or the driven equipment is located inside the space, provided the fluid is pumped outside the conditioned space. This is due to the fact that the heat energy is carried away by the fluid. It is important to use the discretion necessarily. For example, for the direct driven exhaust fan, the case number 3 is applicable, while for the supply or intake ventilation fans, the case 1 is applicable. Note that the heat output of a motor is generally proportional to the motor load within the overload limits. Because of typically high no-load motor current, fixed losses, and other reasons, FLM is generally assumed to be unity, and no adjustment should be made for underloading or overloading unless the situation is fixed, can be accurately established, and the reduced load efficiency data can be obtained from the motor manufacturer. Okay, appliances. In cooling load estimate, the heat gain from all appliances, electrical, gas, or steam should be taken into account. Because of the variety of appliances, applications, schedule, use, and installation, estimate can be very subjective. Often, the only information available about heat gain from the equipment is that on its nameplate. So Q sensible is equal to Qn times Fu times Fr times CLF. Q latent is the Qn plus Fu, where Qn is the rated energy input from appliances. C 1997 as the fundamentals, chapter 28 and table 5 through 9 use manufacturer's data. For computers, monitors, printers, and miscellaneous office equipment, see 2001 as the fundamentals, chapter 29, tables 8, 9, 10, also 1997. If the appliance nameplate provides the power rating in watts, Qn can be estimated as 3.40 times wattage of equipment. Okay. If U is the usage factor. See 1997 as the fundamental chapter 20, table 6 and 7. FR is the radiation factor. See 1997 as the fundamental chapter 28, table 6 and 7. Then CLF is the cooling load factor by hours of occupancy. See 1997 cooling load factor by hour of occupancy. Put Ashley Fundamentals, chapter 28, table 37 and 39. So note 1, CLF is 1.0 if operation is 24 hours or cooling is off at night or during weekend. C2, note 2, set latent load is equal to 0 if appliance under exhaust hood. Infiltration air. Next. Q sensible is 1.08 times CFM times T sub O minus T sub I outdoor indoor. Q latent is the 4840 times CFM times WO minus WI. Q is equal to 4.5 times CFM times H sub O minus H sub I. Take note, yung 4.5 na yan, ang exact niyan is 4.54. Yung gumamit nun. Itong Q changeable and Q total is more accurate ito. More accurate kaysa dito sa Q latent. So yung 4840 ng Q latent is an approximate. Okay. So QCFM is equal to infiltration air flow rate, C 1997 as the fundamentals, chapter 25 for determining infiltration. So T-sub is the outside inside fiber temperature. W is outside inside humidity ratio. H is outside inside air enthalpy with the per pound of dry air. Now heat gain from miscellaneous sources. Meron tayong supply, fan, heat, load. Supply fan or return fan that circulates or supply air to the space and heat to the space or system depending on the location relative to the condition space. The heat added may take one or all of the following forms. Instantaneous temperature rise in the air, stream due to fan drive inefficiency. Then temperature rise in the airstream when the air is brought to static equilibrium and the static and kinetic energy is transformed into heat energy. The location of the fan and motor relative to the cooling coil and space being conditioned determines how heat added to the system. If the fan is downstream of the cooling coil through 2, then the fan heater is added to the space cooling load. If the fan is upstream of the cooling coil, then the fan heat load is added to the system cooling load. Yan. Yun. Kasi after na ng coil, yung pag sa draw 2, after na siya ng coil. Yung sa upstream of coil, before siya, so kan system mo sa ilalagay. The heat energy is calculated as follows. Q is equal to 2545 times P over efficiency 1 divided by efficiency 2. P is the horsepower rating from electrical plant or manufacturer's data. 2545 conversion factor, horsepower per BTU per hour. If fan is full load motor and drive efficiency. F2 is the fan static efficiency. So note G 1997 as the fundamentals, chapter 28, table 4 for motor heat gain. Ventilation air. Ventilation air is the amount of outer air required to make up for air leaving this space due to equipment exhaust, expiration, and or as required to maintain indoor air quality for the fan. See ASHRAE standard 62 for minimum ventilation air requirement. The heat is usually added to the airstream before the cooling coil and has no indirect impact on the space condition. The additional cooling coil load is calculated as follows. Q sensible is 1.08 times CFM times T sub O minus TC. Q latent is the 4840 times CFM times W minus WC. Q total is 4.5 times CFM times H sub O minus H sub C. CFM is the ventilation airflow rate. T sub O is outside dry bulb temperature. T sub C is the dry bulb temperature of air leaving the cooling coil. W sub O is the outside humidity ratio. WC is the humidity ratio of air leaving the coil. H sub O is equal to outside inside air enthalpy. H sub C is equal to enthalpy of air leaving the room, cooling coil, BTU per pound. Wait, tanggalin ko itong inside. Okay, outside air enthalpy. Next is the duct heat gain. Unless the return duct work is ulit. So duct heat gain, unless the return ductwork is extensive and uninsulated or passes over a non-conditioned space, only the heat gain by duct supply is significant. This heat gain is normally estimated as a percentage of the space sensible cooling, usually 1% to 5%, and applied to the temperature of the air leaving the cooling coil in the form of temperature increase. So, ibig sabihin, kung yung return ductwork mo dumaan sa uninsulated saka or dumaan sa non-conducive space, so isama mo rin siya. Pwede siya maging 10% na. Okay? Duct leakage. Air leakage out of or into ductwork can have much greater impact than the duct heat gain or loss. Outward leakage from a supply duct is a direct loss of cooling and or dehumidifying capacity and must be offset by increased airflow or reduced supply air temperature. Leakage into a return duct system causes additional cooling coil capacity, but it does not directly affect the space condition. Commercial type or existing older system can have a leakage from 10 to 50% of the total system airflow. Per energy conservation guidelines, in a new installation, the duct system should not leak more than 1 to 3% of total system airflow. So, sabihin, mag-allowance ka sa airflow. The engineer or designer is cautioned to make sure that the proper allowance for leakages is included in the calculation in order to ensure that the equipment is selected properly sized. Diversity factor. Diversity of cooling load results from not using part of the load on the design day. Therefore, diversity factors are factors of usage and are applied to refrigeration capacity of large air conditioning system. These factors vary with location, type, and size of application. Generally, the diversity factors can be applied to loads from people and light as there is neither 100% occupancy nor total lighting at the time of such other peak loads as peak solar and transmission load. The reduction in cooling loads from non-use is real and should be accounted for. Listed are some average typical diversity factor for large building during occupied period. So type of application, we have office, apartment, hotel, department store, industrial. In case of industrial, diversity should also be applied to the machinery load. Diversity sa light is 0.7 to 0.85. People is 0.75 to 0.9 sa office. Sa apartment, so ito na yan. Calculation of boarded design. Now, next is the supply air calculation na takpan. Calculations for the supply air quantities are dependent on the type of system used. Some generalization and assumption need to be made to assist in the use of cooling load calculation for equipment selection and sizing. For constant air volume with the heat type of system, the design supply air quantities required are based on the peak requirement for each space. However, if the system selected allows for airflow to its zones to vary based on load, the peak load on an air conditioning unit serving several zones or spaces is not equal to the sum of peak load of each zone, but will be that amount necessary to handle the maximum coincident load on the system at a given time. Determine the maximum coincident load may require additional calculation and analysis. So supply airflow rate to a space is based only on the total space sensible heat load. Thus, CFM is 1.08 times Q sensible over T sub R minus T sub S. So wait. Okay, so Q is equal to, CFM is equal to Q sensible over 1.08 times TR minus TS. Where CFM is equal to L pro in cubic feet per minute. 1.08 is a conversion constant, which is 0.244 times 60 over 13.5. 2.4 is specific heat of moist air. 13.5 is specific volume of moist air. at 70 Fahrenheit and 50% RS. For other conditions, solve nyo. Q sensible is equal to total room sensible heat gain BTU per hour. P sub R is equal to room dry bulb temperature. T sub is the room supply air temperature, dry bulb temperature, not necessarily the same as the temperature of the air leaving the coil. Kasi mayroong bypass factor yun. Okay? Hindi siya saturated. And this is 20 degrees below the room temperature, Fahrenheit. So, di na in-explain dito kung anong difference. Pero mali is 20 degrees Fahrenheit. Okay, kung 75 Fahrenheit ang room mo, 55 Fahrenheit ang supply temperature mo. So,